In this screencast, you're going to learn all about the T-distribution, which is actually more useful in modeling and predicting real-world data than the normal distribution. The T-distribution takes into account the uncertainty associated with smaller sample sizes. In a previous screencast, I showed you this flow diagram, where if you know the population variance, then you can use the normal distribution on the left here. We can calculate the test statistic, z, as x bar minus mu over sigma divided by root n. If you don't know the population variance, then we have a second question. Do we have a large sample size? In other words, is n greater than or equal to 40? If it is, then that's big enough that even if you don't know the population variance, you can assume that your sample statistics, your sample variance approaches or is a good estimator for the population variance. And in this case, we can also use the normal distribution. If variance is unknown, but we have a small sample size, then we have to use something known as the T-distribution. And our test statistic, or our T parameter here, becomes x bar minus mu divided by s divided by root n. This is the variance unknown case, and that's what we'll be covering in this screencast. The t random variable is defined as this, x bar minus mu divided by s over root n. Instead of sigma, when we calculate the z statistic, in the t statistic we use s. Its density is given by the following. So hold on, get ready. Here it is. It's this big old function. I wouldn't worry too much about it. This is probably the last time you're ever going to see it because a lot of computing tools have this built in, but we use the gamma function a couple of times in this function. We also have degrees of freedom, which really distinguishes the t-distribution from the normal distribution. In general, if we have n number of samples, then we have n minus 1, or k, degrees of freedom. A lot of times we're going to refer to k. Instead of k, we're going to refer to this as Greek letter nu. The properties of the t-distribution, the mean is 0, so it's similar to the standard normal distribution, and the variance is k divided by k minus 2. As k increases, then the variance gets closer to 1. Let's compare the normal and t-distributions. This top line here, this very top outer one here, that's the normal distribution. If we take a look at the t-distribution with 3, 5, 10, and 25 degrees of freedom, we see with very few degrees of freedom, so this lower one is actually the 3 degrees of freedom, but as we increase the degrees of freedom, then we approach the normal distribution. The t-distribution becomes flatter as n becomes smaller, showing the effect of the uncertainty of the sigma estimate as the sample standard deviation. In other words, if you look out in the tails, the normal distribution is the area underneath that curve, but as we get fewer and fewer degrees of freedom, we actually increase the area or the uncertainty in the tails. And a lot of times, for example, a 95% confidence interval, we split alpha or alpha over 2 into the tails, and so we become more uncertain when we have fewer degrees of freedom, and that usually happens when we have fewer samples. I'll post this Excel file on the course website, but basically we can use the norm.s.dist and the t.dist functions in Excel, and I've created the standard normal distribution as well as the t-distribution for different values of n. And so you can play around with this. If we decrease n to 2 samples, you see that this t-distribution is quite different from the normal distribution. And there's a lot of uncertainty, especially in the tails. As we start to increase the sample size, our distribution starts to approach the normal distribution, the standard normal distribution. But always, for any number of n until you get to pretty high, and the book recommends about 40, we have more uncertainty in the tails for a t-distribution than the standard normal distribution. We can calculate the t-statistic just as you would a z-statistic. Instead of population standard deviation, we use the sample standard deviation, S. The t-statistic follows the t-distribution, as I just showed, with n minus 1 degrees of freedom. This is Table 5 in Appendix A in the text. And importantly, just like I showed you for the Standard normal distribution, the t-value corresponding to alpha probability to the right of it is given this notation t sub alpha comma n minus 1. N minus 1, again, n is your sample size. N minus 1 is equivalent to nu, Greek letter nu. Nu is the degrees of freedom. So t sub alpha comma nu is the t-value corresponding to having alpha probability to the right of it. Because of symmetry, t alpha comma nu is also the same as negative t of 1 minus alpha comma nu. The back of your book has these t tables. It's a little bit different than the standard normal distribution. We've got alpha going across the top. So this is different alpha that's in the tail, the right tail in this example shown. Then we have different rows for our different degrees of freedom, which is nu. As an example, if we had alpha equals 0.025, then t of 0.025, and we had 9 degrees of freedom, we would look up in this table, the ninth row, that's 9 degrees of freedom. This, by the way, would correspond to n equals 10, a sample size of 10. So where those come together, that's the t-value. This means that with a t-distribution with 9 degrees of freedom, a t-value of 2.262 has 0.025 of the entire distribution to the right of it. We can also calculate this in Excel using the t.inv function. Importantly, in Excel, the first argument is the cumulative probability. Instead of 0.025 that you use in the table, you have to use 0.975 because it's cumulative to the left, and we have 9 degrees of freedom. If you plug that into Excel, you'd get the same t-value. Typically, the t-distribution is used for estimating confidence intervals for the true population mean based on sample statistics x bar and s for the variance unknown case. We'll explore confidence intervals when variance is unknown in the next screencast. The t-distribution is also used quite a bit in hypothesis testing, and we'll get to that in a few weeks. Thanks for watching.